If you're coming in, excuse me, if you're coming in, the exams are right here. I'm going to put them here. Is that all right? Just grab your exams, and the grade is just add up the points I took off and subtract from 100. I've posted the grade on Canvas for you already. Come on. Come on. Come on. Oh. Let's go. Let's go. Let's go. Oh my goodness, why is this so slow? Okay, let's go through this. I don't intend on doing this for every mini exam, but at least for this first one, let's talk about it. What you'll see here is the exams are up here. If you just came in, over there. Okay. What? Oh no, I'm saying to everyone. Oh. Okay, so over here, what you'll see is the student's overall grade. And then for each problem 1, 2, 3, 4, 5, and 6, how many points I took off for that student. And this is just ordered from highest grade to lowest grade. So for example, this particular person got no points taken off on number 1, 6 points off of number 2, nothing off number 3. You get it? And then at the bottom here, you can kind of look at this and see what problems I took the most points off of. So it looks like number 2 was... Number 1 and number 2 were the ones that I took the most off. And then also number 6. All right? And then the class average was a 77 with a standard deviation of 20 points, which is a pretty big standard deviation. Not the biggest I've seen, but pretty big. This is a graph of the A's, B's, C's, and D's. We had 11 A's, no B's, 6 C's, 2 D's, 5 F's. And then you can kind of see here where there's like this group. You've got this cluster of students here that got, A's. Then you've got your C's in here. And then you've got the, D's and F's in here, right? So I would be concerned if you're in this group right here. I'd be a little concerned. Because this was a take-home exam. Some of the things that I was kind of disappointed to see, I'm happy to see that we had a lot of hundreds, okay? I'm happy to see that. But the things I'm disappointed in are neatness, things in order. This is a take-home exam. You know, you should turn that in. It should be like your final draft work that you're proud to hand in to me. And when it looks like it's just a bunch of random things thrown together at the last minute, then, I mean, it doesn't affect how I grade it, but you know, you need to work on it. The instructions say neat, in order, stapled, all that's in the instructions, so make sure you do that. Anybody have any idea what the yellow highlights are? What's that? Awesome students?
Office hours?
No? What do you mean?
People who came to reach out to you?
Kind of. The one in the yellow, the students in the yellow are students who either worked together or came to work with me. Okay? I think it speaks for itself. Nobody who worked alone, right? Nobody who worked alone is in that group. Everybody who worked together or came to see me scored an A on that test. All right? So I'm trying to encourage you. Get help. Work with each other. Come see me, right? Okay, that's it. I don't have the second mini exam ready for you. My plan is to try and get that out to you probably, what's today? Wednesday, so probably Monday we get that to you. All right? It's ready, I just didn't print it.
For the midterm, are we going to have a review?
Midterm review, not really. I mean, you mean like we're going to spend a whole class like talking about it?
No,
Or
like you're going to...
like hand you a piece of paper?
Yeah, like here.
Probably
here's
not.
this.
I'm going to tell you, make sure you study your homework. That's what I'm going to tell you. Because the midterm is going to be over homework. The question came earlier, you know, is the midterm going to be problems like the mini exam? And it's not, right? It's going to be like homework problems, and I promise you that. It's going to stay within that level. Now, I may narrow your focus a little bit, okay? I may, and like we were talking about that problem earlier, if I give you an equation, ask you to classify the surface, I'm going to give you the list of surfaces, that one off that page that has like the summary. I will give you that. You won't have to memorize all the surface formulas.
Would it be like multiple choice?
It might be. It might be, here's the surface, match it to its graph. I doubt it, but. Okay, any questions over this exam? Like I said, if you have any questions on why did he take off 13 points? Like, come talk to me. Question?
Show us how to do B.
How to do what?
B. Or, was it 2? There you go.
I will show you if you come visit with me in my office.
Okay.
Yeah, we just don't have time for it here.
Oh, that's fine.
Yeah, but I'd be happy to go over that. All right, back to business here. We were in 10.7, and we're still trying to get out of 10.7. I'm confident we can get out of 10.7 today. Hopefully we can get into 10.8. I don't know. Let's take like 30 seconds to 1 minute. Do y'all have any feedback from me on the mini exam? Like, what's your sense after doing the mini exam? Any comments? I'm not going to hold them against you.
I like the time constraints.
You like the time constraints?
Yeah, like that in Cal 2, when I used to want to take the exam, it was kind of like do like 3-4 days later.
So you liked that you had time to do it?
Because I got a student.
Yeah, like-
So that extra time really.
Okay.
I'll agree with that.
Okay. Yeah, I usually try and give 2 weeks for each one. But the problem with that is we may fall a little behind in terms of you may be doing a mini exam, but we're like already past that material here. So your mini exam is covering stuff that was like from last week or the week before. So that's the only thing about that. Any other comments? The whole goal of the mini exam is to make you think more, right? To help you become better problem solvers. I know I had some really good students who got like 14 points off on a problem. And I know those students are capable of doing that problem. So what I would say is, even if you feel really good about your answer, don't be that type of student where it's like, you know, you're like, well, I don't need help. I don't like asking for help. Just go ask, because I mean that could cost you a lot of points. If your perspective that you think is right is completely off, the fact that you can verify that with me, you know, to say, hey, I'm approaching it this way. Is this good? And I'll tell you, you need to rethink that. You know. All right, let's go. Anything else? No comments? If you just came in, the exams are right there at the table there. All right, we are continuing 10.7. We were talking about vector functions, and we had talked about limits and derivatives. And now we're going to continue with that, and this is just an interesting result. It says that if you have this particular two-dimensional vector function, cosine t sine t, which draws a circle, that we want to show that r of t is orthogonal to r prime of t for all t. Now remember, r of t is a vector that goes from the origin to the point on the circle. So at some point in time, right, we're going to have a vector r of t here. Right? And so even though we look at it as a point, it's actually a vector from the origin to that point, right? That's r of t. And what we're trying to show here is that the derivative, which is another vector, r prime of t, that they are orthogonal all the time. For this particular vector function, we need to show that it's true. So how would I show that? Show that their dot product is 0, right? So I need to take, I want to show, I'm going to put WTS, which means I want to show that r, the vector function r of t, dotted with its derivative, is equal to 0. If I can show that, I'm done, right? Okay, so what is r of t? It's just that vector cosine t sine t. And what is r prime of t? Negative sine t cosine t. Because when you take the derivative of a vector function, you just take the derivative of its components. And now what? Dot it? So what would happen if you dot this? You get, what, cosine t times sine t, but it's negative, right? Because cosine, negative sine. And then plus now sine t cosine. This is obvious. Sine t cosine t. They just wipe each other out, right? 0. Check. This is just the picture of it, all right? This is just me showing you what that looks like. As you move the vector around, as you change t, you can see that the derivative is always running orthogonal to that. Trevor, the exams are right there. You can pick yours up if you like. All right, let's look at the next. This next one I think is really interesting. This one is saying, show that if the magnitude of a vector function, any vector function, right? It's not telling you what the vector function is. It's just saying, show that if the magnitude of some random vector function is a constant, is equal to c, then we have the same result that we just had right there. That the vector function itself is orthogonal to its own derivative. So in the previous example, when we drew that circle, couldn't we say that the magnitude of r was constant? Because that's the length of the vector function. And if it's drawing a circle, then the length of each vector is always the same. But this is saying that will work for any vector function. It doesn't have to be drawing a circle. As long as the distance from the origin to the curve always stays constant, then the derivative will always be orthogonal. How in the world can you show this? I mean, what do we have to show? We want to show the same exact thing, right? We want to show that r of t dotted with its derivative is 0. Do you understand why this is going to be a problem? Like, do you know what r is? So do you know what its derivative is? So how do you show that, right? It's difficult. This is one of those problems that this is kind of a problem. Once you see me work through it and you ask, like, what do math majors have to do? This is kind of like, this is the way math majors have to think about a problem like this, all right? And once you see it, you'll be like, wow, I don't think I would have ever thought of that. And then, you know, that's how we train to become mathematicians. You have to start thinking a certain way, right? So here's what I have to show. The only thing I know is this, right? This is the only piece of information that's been supplied to me, right? That right there. So I'm going to write that down. I'm given that the magnitude of the vector function is a constant. And then I look at that, and I'm like, how in the world can I somehow use this over here? Does anybody have any ideas? I don't expect anyone to, but does anyone have an idea? Square root of r squared. What do you mean? Like rewrite the definition of this? Like what does the magnitude mean? We could. I don't know if that's going to get us anywhere.
Or what you can do is you can rewrite the d prime to dr over dt just to get to your c.
Maybe. Maybe.
Like put it into a differential equation maybe?
Mm.
I don't know.
That's not this is not your normal multiplication though here, right? This is not our normal multiplication. These are vectors being dotted together. So it's a different type of.
Could you use its components?
Okay, so you could maybe break it down to its components, which you don't know, right? You don't know what they are.
Right. So we
But-
could say like T, yeah, T1 or T2.
Yeah, so you could say, hey, this is f of t, g of t, h of t, right? That's what r is. We're assuming it's three-dimensional, and it's being dotted with f prime t, g prime t, h prime t, right? And we want this, right? We want that. We don't know if it is, but we want that to be 0. So if I dot these, right? Do you understand what I wrote here? So if I dot these, it's this times this, plus this times this, plus this times this, and I need all that to be 0, don't I? But all I know is the length of the the magnitude of the derivative is a constant. So look, like I said, I didn't expect anyone to see this, all right? This is valid, okay, but I'm pretty sure we're going to just get to a dead end here. Let me show you how it's done, and like I said, you'll go, wow, I'm not sure I would have ever thought of that, all right? Okay, so watch this. This is what we're given, right? So do you agree with this? Yes? Okay, do y'all remember what the magnitude of a vector squared is equivalent to? It's that vector dotted with itself. So do you agree with this? That this is r of t dotted with r of t equals c squared. So you have to go back and look at when we were talking about vectors and dot products. I gave you this. U dotted with u is equal to magnitude of u squared. That was a property of dot products. So what I'm doing is I'm doing that backwards. And I'm going from here to here. Do y'all see that? So far y'all agree with these statements? Now at this point, it's hard to see how we're actually going to get from this to this, right? So see if you agree with me on this. If I take the derivative with respect to t of the left side, and then the derivative with respect to t on the right side, what is the derivative with respect to t of a constant squared?
0.
It's 0, right? This is 0. So the right-hand side of this equation, is 0, which is outstanding because up here I have a 0, right? And then how do we take the derivative of a product rule? Well, I gave you that property at the end of class last time. I brought up a bunch of properties, and what you use is the product rule here. So what you do is you take the derivative of this one, dotted with this one, plus the derivative of this one dotted with this one. But they're the same functions, right? So I get this. I get the derivative of the first one, r prime t, dotted with r of t, plus, same thing, r prime t, I'm out of room, dotted with r of t again, equals 0, right? Now, those are exactly the same expressions, aren't they, on the left side? So I have two of them. These are identical. So 2 r prime of t dotted with r of t equals 0. Now what? Divide both sides by 2, and what do you get?
R prime of t.
What we wanted to show. Right? So this is a completely, I don't know if it's completely unnatural, but to go, oh, here's this and then to this is not something that is usually obvious to somebody. All right, so I would never ask you a problem like this where you're having to like make this huge leap, but I want you to see it, okay? Because this is the way mathematicians have to think. Now, they don't think like this initially, but they take enough classes, they start having to think that certain way, and you know, you're given that and then you start doing different things to it until you can somehow get to what you're trying to get to. Okay, that's it. So any vector function that maintains a constant distance from the origin, the derivative, right? That derivative vector will always be orthogonal to the vector function itself. So obviously a circle does that, but another example of like a three-dimensional one would be, imagine I had like a string, right? A string with like a ball on the end of it. And I start swinging that around, okay? Now, I can't move this hand, but imagine I could somehow swing it so the ball's moving around, right? My hand's just fixed, rotating. The string has the ball, right? That path, the ball is always the same distance from my hand, right? No matter the path of the ball, if at any point you try and pull that tangent vector off, it's going to be orthogonal to my string. That's what that little that's kind of a theorem, right, is saying. All right, moving along. All right, now we're going to focus on some applications of the derivatives. We've looked at how we can get them. We know that if you have a curve, and it doesn't matter if this curve is three-dimensional or two-dimensional, right? That if we pick a point on it, we can find that tangent vector by just taking the derivative of the vector function, right? That's what last class was about. But now, what are some other applications of this? So what I'm going to do here is I'm not going to follow my notes exactly the way they are here because it'll take too much time. I want to cut back on the time for this particular demonstration. But I have defined two different vector functions, r1 and r2, okay? Here they are, t squared and t squared t to the fourth. And I claim right now that they will draw the exact same curve. They draw the exact same thing. So let's just try it. Let me try and graph these. These are two-dimensional, aren't they? Let's plug in 0 here for t, and what do we get? 0, 0, right? So there's the point there. How about if we plug in 1 here? 1, 1, so 1, 1, we would have a point here. Now, remember, there's a vector going to it, but we're just going to draw the point. Then if I plug in 2 for t, what do I get if I plug in 2 for t?
2, 4.
2, 4. So I go out 2, up 4, and I'm here. And if I keep doing this, I'm going to draw this like a parabola. Y'all agree? Now, can you get the same points from this graph here? Okay, so 0 would give you 0, 0, right? So I'm trying to do this one now. This one right here. There's that point's there. How about this point? Is this point there? What would I have to plug in for t to get that point? 1, right? Okay, can I get this point right here? Remember, that's the point 2, 4. Can I make that happen? What do I plug in for t? Square root of 2. Right, if I plug in the square root of 2 for t, I square it, I'm going to get 2. Square root of t, 2 to the fourth will give me 4. So I should be able to get that point. Is that enough evidence for you, or are you convinced that these would draw the same exact curves? Yes or no?
It would, just that difference.
Okay, so that's my next question was, so what's the difference between the two? If they draw the same curve, then how are they different? It's going to have to, it has to do with, if we imagine t being time, it's how fast the curve is drawn. It's a little too big. I'm trying to get these side by side. So here I have the two graphs side by side. And what I'm going to do is I'm going to plug in to each of the curve, the vector functions, I'm going to plug in the same time, all right? So time is going to be up here. Let me pull it back. Right now time is 0, and do you see? This is the R1. This was the one that was t squared. This is the other one, t squared, t to the 4th. At time equals 0, they're both at the same place, right? How about at time equals 1? Or here's 0.25. Let me go to time equals 1. At time equals 1, they're at the same point, aren't they? What about time equals 2? Are they at the same place? No. This one's right here at 2, 4. But this one over here is already jumped all the way to 4:16, right? And if I advance time, you can see that even though this one's drawing the same curve, this one's drawing it faster. And this is important because when we talk about things moving through space, we're not interested in just the path that they're traveling through, but how quickly they travel through that path, right? Maybe they travel and then they slow down and then speed up. And that tangent vector is going to be the thing that actually helps us determine that speed, right? But understand the picture though? Understand how these are different? All right. So, if r of t is a vector function, this is an application, all right? If r of t is a vector function, which represents the path of a particle or an object through space, then we call it the position function. So the vector function r of t that we've been looking at now, or in the past, if it describes where some object is, then we call it a position function. And if we take its derivative, we will call it the velocity function. And we can label it v of t. Okay, it's the first derivative of the position function. The magnitude of the first derivative is the speed of the particle at that particular time. What about r of t, I'm sorry, r prime of t, without the absolute value, what is r prime of t? It's the velocity, but what is it?
Vector.
It's a vector, right? And vectors have what two things? Direction and magnitude, right? So when we talk about the velocity of an object, you're talking about a vector. When you talk about the speed of an object, you're talking about the magnitude of that vector. So a lot of times, if I go to like my college algebra class right now and I say, hey, what's velocity? They'll say it's speed. And in that class, it's probably okay. But if you've taken physics, you understand that velocity and speed are not the same things, all right?
So you could have constant speed and like your velocity couldn't change it?
Absolutely. Yep. Right?
Velocity.
You could. You could have a constant speed with a changing velocity. But that means that your magnitude's staying the same, it's just your direction's changing. How about if we take the second derivative? Well, the second derivative is the acceleration function. And the second derivative is a vector again. A vector function, I should say. All right, the larger the magnitude of the absolute value of the first derivative, the faster the particle is moving at that point in time. Okay, so I had some examples here. I don't know if I want to look at all of these. Let me see what I have after this. I'll come back to that if I feel like we need it. Those 4 problems were just kind of like review problems from everything we've talked about up to that point. There's nothing that has to do with, well, I think there's one that has to do with velocity. But is there anything new, though, mechanically, that we have to do? I mean, if I give you a position function right now and I ask you for the speed of the object at a particular point in time, what are you going to do? Take the derivative, plug in the point, or plug in the value of t, take the magnitude, and you're done, right? So there's nothing new mechanically here. It's just now we're putting meaning on these things. I want to get to integration, though. So if you have a vector function, right, we should be able to integrate it. If you can differentiate it, you sure should be able to integrate it. And luckily for us, the integration is as straightforward as the differentiation was. If you want to integrate a function, a vector function r of t, it has the 3 component functions, possibly 2. Okay, but I like to talk about the 3 case because it's I guess covers the 2, I guess. So with 3-dimensional vector function, if I want to integrate that function, then it's going to be this. So really all you're doing, here's the notation we would use. You have the vector function integral from a to b with respect to t, because that's our independent variable. So that is still a vector, isn't it? Look at that. It's still a vector. But you're going to integrate each of the component functions with respect to t from a to b. What should this spit out? If I have a and b here, if those are numbers, and this is a function, I integrate this, what should this spit out? A number. That should spit out a number, that should spit out a number. But it's still a vector, right? It's the 3 separate components of a vector. Do you have to put plus c? Yes, you do. If they were indefinite, right? But remember, definite integrals don't have the plus c. Remember that?
Yeah.
Okay.
I was just asking.
We're going to have to deal with it. Trust me, we're going to do it. We're going to do it here, right? Well, after this one. All right, so here is an example. All right, if r of t is e to the t root t minus 1, and then natural log t, those 3 component functions, then find the integral from 1 to e of r of t dt. So I have to do 3 separate integrals here, don't I? So I'm going to do this like scratch work, all right? I'm going to do all my scratch work over here, and then I'll write my answer down. I need to do the integral from 1 to e of e to the t dt. Let me do that one first. What is that? What's the antiderivative of e to the t? Itself, right? So the notation that hopefully you use also is you write e to the t, then this bar, and then you put like 1 and e there. Yes. Sometimes you'll do t equals 1, t equals e. It just depends on your background. I know in my Cal 2 classes I didn't put the t, but I'm going to start putting it now. All right? Y'all hear me? I'm going to start putting it now because later on we're going to have to keep track of that sort of thing. So it's always been assumed that we're plugging in 1 for t. But later, as we get more variables, we're going to need to know what we're plugging in for. All right, so now you plug in what? E first, so e to the e, and then you subtract from that e to the 1, right? Okay, that's a number. That'll be the first component to my answer, but I'm just going to leave it there. Next one. I'm going to integrate from 1 to e of t root t minus 1 dt. What is that? A u sub?
Well,
Integration by parts.
Integration by parts.
no, it's an integration by parts because you don't have the derivative.
What do y'all think?
Integration by parts.
I've heard u sub, which is always the easier way, right? If you can get it to go u sub. I'm going to do the indefinite integral over here and then get the answer and throw it in there. Let's see if u sub would work.
Well, can you force the t to go in by squaring it?
You can force the t in, and it would become t cubed minus t, but then it's under a root, so how do you...
Well, that would be for like u sub, but I mean, you can't really use it because there's no
What was your u sub going to be?
t minus 1.
T minus 1?
Or you can do
That's actually going to work. but I don't think it's going to work for the reason you think it's going to work. From what you're saying, we don't want to force the t in.
Yeah, I'm not.
All right, so let's try this. If we let u be t minus 1, then du is dt. Again, this goes back to how you learned this in Cal 2. You may have seen some different notation. Does this look somewhat familiar?
T equals u plus 1.
So now I need to rewrite this. That's going to become u. dt is going to become du. I just need to rewrite the t. But I can go right here to get the t. T is u plus 1. So this integral now becomes integral, parentheses u plus 1, square root of u du. And now we'll distribute. So I'll do one more line. This is integral u plus 1 u to the half du. Something else I saw in the mini exams that when I saw it, I was like, that's totally me. That was me like back when I was in calculus. I used to write my V's in my U's like this. And it was a real problem for me. Jonathan, yours look exactly like mine used to look. Yeah. Yeah, so what I finally figured out I needed to do is do that to my U's. In my V's, I kind of over-exaggerate them. I kind of curl the right side of them. They almost kind of look like R's if I'm not careful. But there's all these little things you have to do if you're going to be doing more math that you have to pay attention to. Like T's, you should probably curl your T's so they're not look like pluses. You should probably strike your Z's so they don't look like 2's. Those are just little things that you're going to have to change for yourself to help you. All right? All right, so, sorry. Back to this. So once we're here, distribute this through u to the 3 halves plus u to the half, and then du. And then now we can just do that term by term. So what's the antiderivative of those here? 2/5 u to the 5 halves plus 2/3 u to the 3 halves plus some constant, right? But I'm not going to need the constant because I'm going to plug this back into a definite integral. So I don't care about the constant right now. And I do need to replace the u, right? What was u? T minus 1. So I think I'm ready. Here goes. This should be equal to 2/5 t minus 1 to the 5 halves plus 2/3 t minus 1 to the 3 halves. And then I'm going to evaluate that 1 in e, right? So you can imagine that on a take-home mini exam, I might ask you to demonstrate your proficiency in integration, right? I'm probably going to give you something to integrate that's going to take a little bit of thought. Okay. But on the in-class test, it would be, you know, U sub. This to me is totally fair game on an in-class test. That's just basic U substitution. All right, keep going here. Let's plug in. When I plug in E, it's just going to be some ugly stuff here. It's going to be 2/5. It's going to be E minus 1 to the 5 halves. I'm not going to get my calculator out. I'm just going to leave it like that. 2/3 E minus 1 to the 3 halves, right? That's what I get when I plug in E. Minus, now let's plug in 1. And when I plug in 1, things are good, right? 0, 0, it's gone. So really, that's it. That's all I have, right? So this is the second component of my answer. I'm going to leave it like that. That's the exact form. You could factor and stuff. Just leave it, all right? Last one. Antiderivative of natural log t. So I need to do integral from 1 to e of natural log t dt. And the antiderivative of the natural log of t is not 1 over t. It is t ln t minus t, and then 1 to e. Now, my Cal 2 students, I guarantee did that in class at some point. And I think I even said you can write it on your formula sheet, but to remember it, because it does come up like it just did. All right, so now we plug in E. Let's see what happens when we plug in E. I get e, natural log of e is 1 minus e. Oh, that's 0, right? Okay. Then I say minus, and then I plug in 1. So 1 times, what's natural log of 1? 0, so I get 0 minus 1. So that's the whole thing there is just going to turn into 1. So the answer to this question, all right, the answer to this answer right here is the vector. It's a vector. And because I don't want to write this all down again and save us some time, it's a 3-component vector, right? This answer is a 3-component vector. The first component is this. The second component is this. And the third component is 1. I'll write that one down. There. Understand?
That's 12.4, and then that's...
Yeah, but I don't want the decimal.
Yeah.
I want the exact. But that, yeah, you could get them as decimals. Understand? All right, that was just to get our old integration brains going again. Look at this one. One of the things you should have learned in Calculus 2 is that if you start with a velocity function in Cal 2, that if you take the antiderivative, you go back to the position function. And the same thing applies here with vector functions. If the derivative of r of t is this vector function, and I tell you that r of 0 is the vector 1, 1, 1, then tell me the position function. So what I've given you is some information about the derivative of r, and I've given you what we call an initial condition. And from that information, we need to be able to get back to the original r function. So let's try this. Yeah, I know r of t should be equal to the antiderivative of r prime of t with respect to t. Do we agree with that? Now, we will be off by a constant here because this is not a definite integral, right? But let's try this. Let's r of t is equal to, how do we take the antiderivative of this? 1 by 1, right? 1 by 1. So what's the antiderivative of t? 1/2 t squared, right? So what I just did right there is I was trying to integrate this one. I just did antiderivative of t dt, right? That's what I just did. And that's 1/2 t squared. But aren't I supposed to do plus c? Yes? I mean, I am supposed to do plus a constant. But I'm going to do 3 of these integrations, 3 separate ones. I'm going to get 3 separate constants, right? So what I'm going to put here is 1/2 t squared plus c1. All right, so right here, normally we call it c, but I'm going to call it c1 because it's the first integration that I did. Now I need the second one. Antiderivative of e to the t is itself e to the t plus a constant of integration c2, right? Next, antiderivative of t e to the t. Integration by parts. You got to do integration by parts on that. Now I trust that everyone can do that because you've passed Cal 2, but maybe it's been a while, so we'll do it real quick. Again, everyone's going to have their own little method that they learned in their Cal 2 class. I'm not here to reteach integration by parts, but the way that I do it is I set up a table. I put u here, dv here. Those are the 2 things I have to fill in. So what am I going to choose for my u? T. And my dv is going to be e to the t dt. Don't forget the dt. And then to fill out the rest of the table, what I need to do is differentiate down to get du, and I need to integrate up to get v. So the derivative of t is straightforward. It's 1 or dt. 1 dt. And then the antiderivative of this is just e to the t. And then, did y'all learn this thing? uv minus integral v du. Ultraviolet, how many of you heard the ultraviolet minus voodoo? Yeah. Okay, some of you have, some of you haven't. That's the formula that we use for integration by parts. So this integral will become u times v, right? U times v. So this times this, so t e to the t minus the integral of v du. So these two multiplied. So e to the t dt. And that integral is easier to do, right? Antiderivative e to the t is just itself. So we should get t e to the t minus e to the t. That's what goes here. Plus C3. T e to the t minus e to the t plus C3. Questions? So far I know the position function, but I know it within constants. I don't know what these constants are. But that's where this information comes into play, right? It tells me that when I plug 0 into the position function, it should spit out 1, 1, 1. That means when I plug in 0, and I'll do this in a different color so you understand that I'm now evaluating this vector function. These markers are awesome. I didn't tell you all about these markers, did I? No. One of my students last semester gave me these, I guess, as a gift. I'm not sure. I got you these really nice markers. So they're really good. They come out real nice, but man, they're hard to erase. They're really hard to erase. Yeah, I shouldn't be complaining, right? Because most of the other ones never work. Okay, so I want to know what C1, C2, and C3 are. Understand? I'm trying to figure out what are these constants. If I can nail these constants down, then I have the actual position function. Using this information, I know that R of 0 being 1, 1, 1 implies that when I plug in 0 for t, right? When I plug in 0 for t, let's try that. I get what? 0 here, gone. I just have what? C1, right? What happens when I plug in, be careful here, what happens when I plug in 0 for t here? I get 1 plus C2, right? E to the 0 is 1. How about if I plug in 0 here for t? 0 minus 1, so I get minus 1 plus C3, right? This vector needs to be equal to what? 1, 1, 1. And so that means that C1 has to be 1, 1 plus C2 has to be 1, and negative 1 plus C3 has to be 1. So that's three little equations that we can solve. C1 is 1, 1 plus C2 is 1, and negative 1 plus C3 is 1. So that one's already solved. This one says C2 is 0. And this one says that C3 is 2. So my final answer here is R of t is the vector 1/2 t squared plus C1, but C1 is 1, so plus 1. And then e to the t plus C2, but C2 is 0, so just e to the t. And then finally, t e to the t minus e to the t, what? Plus 2. That is the precise position function that we are looking for. You like this better or the other one? At the points, yeah. All right. You see how I do here erasing. All right, so this next note just says that the antiderivative of acceleration is velocity. Right, if you take the antiderivative of the acceleration function, you get the velocity function. And then if you take the antiderivative of the velocity, you get the position. And that's, again, something you should have seen in Cal 2. This problem starts out with an acceleration function and asks you to get all the way back to the position function. I'm not going to work this one out. Let's just talk through it. What would I do first?
You would take the
Antiderivative of a to the t, which would give me the velocity. And I would have three components, right? Each one of those would have within it c1, c2, c3. I would then use this information about the velocity to get c1, c2, c3. Then I would have velocity, right? Then I take the antiderivative again. When I do that, I'm going to have three component functions, and I'm going to have, again, c1, c2, c3. And I'm going to use this information to get the position function. So it's just two of what we just did. All right. All right, that's the homework. It looks like a lot, doesn't it? I don't know, why are there two sets of homeworks up there? It's weird. Same page.
Which one do you want us to do?
Yeah, I mean,
Pick one.
just do it all.
Just do it all.
Just do it all. Yeah.
1 through 5, 7.
No, just do 1 through 11, 12, and then 15, 17 through.
Wait, so you want us to do them all?
Is that in the notes?
Yeah.
Like when you print out the notes, is that in there? Yep. Anyone who print? Yes, it is. Has both of them written down, messed up like that?
Yep.
Okay. All right, so that's in your notes. I don't need to keep it up here. That's it. We're done with 11.7.
Except I think it's 568 and 586.
Oh, it's 568 and 586?
568 and 586.
Let me just double check it. 568 is not a page, so that's a typo. So 589, yeah, it's 589 for both. So fix that, please. All right, some more applications here. We get to something somewhat interesting. If you're kind of waiting for Cal 3 to feel like something different, I think it's going to happen in Chapter 11. I think that's when it's going to start to feel like that's when we're going to go and like go into three-dimensional space and like look at things. And right now we're still just doing differentiation integration. It's not really anything that different. The vector functions, I guess, are new, but okay, arc length and curvature. All right. Suppose you have a vector function, a two-dimensional vector function. We'll start with two-dimensional, right? It draws a curve, right? If I restrict the time between two constants, that means you're going to start drawing and then you're going to stop drawing at some point, right? And you're going to have this space curve, two-dimensional in this case. Then it makes sense that we should be able to find the length of that curve, right? Which we call the arc length. So that's like you take it off the piece of paper and you stretch it out and you measure its length. And the formula for it is right here. The length of the curve is the integral from a to b of the magnitude of the derivative of the vector function. Now, what is the magnitude of the derivative of the vector function? Well, the derivative of the vector function is f prime g prime, because it was two components. So the magnitude, you take them, square them, and then take the square root. So this is just the same thing as this, just written out for you. And I say we can look at this as the infinite sum of infinitesimally small tangent vectors. Find the arc length of this vector function from t equals 0 to 2 pi. Does anybody know what it should be? The final answer? 2 pi. So where are you getting that from? This is just the circumference of this circle, right? This draws a circle. The arc length, if we start at 0 and end at 2 pi, we're going to draw the whole circle, aren't we? And this is just basically asking us for that length. And the circumference of a circle is pi times the diameter, or 2 pi r. The radius of this circle is 1 because there's a 1 in front of the cosine, 1 in front of the sine. Yes? Okay, we're going to verify that. It's going to be, I think it's going to be a pretty straightforward verification though. All right, so what do I need first before I start computing anything? I need the magnitude of the derivative. So let's take the derivative quickly. Negative sine t, cosine t, right? And now it's magnitude. Magnitude of this is the square root of the sum of the components squared, negative sine t, I'm going to square that, plus cosine squared t, oops, cosine t, I'm going to square that. And look at that. Isn't that nice? Sine squared t plus cosine squared t. That negative doesn't matter, right? Because you're going to square it. And that's the Pythagorean identity. Square root of 1 is 1. Square root of 1 is 1. So I'm just integrating 1, right? That's all I'm going to integrate. And I'm going to integrate 1 from where to where? So what are restrictions on time here? 0 to pi. I'm integrating 1 dt. The antiderivative of 1 with respect to t is t. So there's just t evaluated from 0 to 2 pi. Plug in 2 pi, you get 2 pi. Plug in 0, you get 0. 2 pi. That matches with the formula, right? The formula was 2 pi r. If the radius is 1, we should get 2 pi. I know my Cal 2 students, we actually proved in Cal 2 the formula for the circumference of a circle, radius r. We proved it, and if you go back and look at that proof, it was a lot more difficult than this. A lot more difficult. So this is super clean, isn't it? Isn't this very clean? Watch, if I change this to r cosine theta, r sine theta, isn't that a circle with radius r? Okay, so what would change here? Negative r, r, right? What would change here? Negative r, r. What would change here? R squared, r squared. What would change here? I could pull out the r squared and then pull it out of the root. So I'd have an r out here, and this would just become r, right? And so now I come over here and I'm integrating r with respect to t. The antiderivative of r with respect to t is rt. And then when you plug in 2 pi, you get 2 pi r. And there's your general formula. So it's super clean. Trust me, if you go back and look at your notes and what it took for us to prove that in Cal 2, it was, I'm not going to say it was monumental, but it was a lot of work. This is, with the vector function concept, you can do this a lot easier. Okay, cool. That's a picture. Now the same thing applies for three-dimensional vector functions. If you want to find the arc length of a three-dimensional vector function, you're going to have three component functions, f, g, and h. You're still going to need to limit your time between a and b. And the only difference here in the formula is that when you look at the magnitude of the derivative, you now have that third component squared in there. That's the derivative of the third component squared. And that's it. We talked a little bit about this vector function last class. This draws a spring.